Hello all and welcome back. In this video, we want to now implement the binary search tree class. Okay. So many of you might be thinking that why haven't we implemented the same for previous generic trees or binary trees? We have studied those kind of trees as well, right? Well, the reason for that is, let's say you are given a normal binary tree. Okay. So it is 50 here and let's say it is some 5. And if I ask you to now add say 20 to it. Okay, let's say I'm asking that, hey, add 20. Do you think like it's doable? Like there is some default way you can do that? Like I see that there are 4 positions where this can be added, right? So it doesn't actually make any sense that you will be creating an insert function and then you will be saying that, hey, can you insert this particular node into your tree? And I don't have any logic defined. Similarly, for deleting any node, okay, or overall for any other operation, we anyway have to go to each and every node, right? But for the binary search tree, we have the property which we can use. So let me write that down as well. For binary tree and generic trees, no logic is defined, right? So no major logic is defined, because of which we need to make sure that for BST we are able to add it. And actually I can help you visualize the same as well. Like always, I have this visualizer for you. In this, what we are trying to do, let's say you add 10 as a node. Okay, so I'm saying insert. 10 is inserted. Now let's say if I want to add 20 and I click insert. 20 is added here, right? Now say I want to add 5. Now you will also be able to think that, hey, where this 5 should be added, right? So 5 is added here. Now let's say I add 9, insert. So this overall structure, right, it has a meaning to it. It has some property which it is trying to follow. And we have to do the same thing. Okay. So there are going to be 3 major functions which we have to implement. So 3 major functions are actually there. 3 major functions or methods, we can say. Okay. They will be methods only. So let us keep that in line. They will be methods, right? First is going to be insert. Second is going to be search. And third is going to be delete. Now we can have the traversal as well with respect to post order, pre-order, in order, but I'm pretty sure that you all will be able to do that. These are the 3 major functions which we have to perform on our BST class. Okay. So when a person says insert, you will have to always make sure that we are maintaining that it should remain a BST. Is BST will not be a function. The reason for that is we are taking the onus that, hey, I will be maintaining this as a BST. Okay. No matter what operation you do, if you're inserting anything, if you're deleting anything, I will be making sure that at the backend, the whole thing is saved as a BST. Okay. So that's the overall idea, everyone. Now let us move forward and discuss a little bit on this, right? And you will see that these were the 3 methods which were there on the visualizer as well, right? So let me go to the visualization. In the visualization, if we see here, search, insert, and remove, right? So if let's say I search for 9, it will tell that 9 is in the tree, right? These in order, pre-order, everything, I'm pretty sure you will be good to write. So in order, it is giving us, right? Great. So now let us move forward and see how will we overall implement this particular class, right? Great. So first I have to create a binary tree node or binary tree search node. You can create it anyways. Okay. So let us create it BST node only. Let us keep it as direct BST node. So this we have written a lots of time, def init self, and you will be giving me some data. Now self dot data equals data. Self dot left. Self dot left will be none. And similarly, self dot right is none as well, right? So this is our BST node normal. Now what I have to do, class BST. Okay, so this is the major class which I have to implement, wherein I will be giving you these functions. Okay, great. Methods, not function. First is constructor. So let's say if what is exactly the constructor here, right? Let's go back to the visualization. If I just refresh it, what are we seeing? We are seeing that it's an empty tree, right? Now this is the overall condition which should be there in my constructor, right? So I think we have seen this a lot of time. We can say self dot root is null. So as of now, it is empty. Okay, great. Now we want these functions. Insert, where you will be giving me some data. So we want these methods. Search, again you will be giving me self, sorry, I will have, and you will be giving some data which I have to search. And finally, delete, where again you will be giving the data. Okay. So these are the three functions, sorry, methods which I have to implement, right? I think search one is something which we have done already. Search is some method which we have done previously. So this is where I asked you to implement the search and we discussed the same in length. Okay. So overall you would have completed this, but there is some caveat which I would like to discuss. Okay. So let us first complete search. So pay attention everyone, what's going to happen in search, and let me just copy it down here so that we can complete it. Great. So when I'm doing for search, let us pick up search as the first one because that is something we have already done. If I ask you to search for a particular node in my BST, what exactly do we have to do? Let me draw it again and nicely. Yeah. We have to go through nodes, okay, based on some condition, and then say if I'm able to find that particular node or not, right? So it is based on checking the value with and comparing that with the root. And we used to call one half, right? We used to call on either the left half or the right half, right? So that is something which we used to do when we used to search for our BST. So let us write the code for that. First thing is if root is none, okay? So we are taking self, I will have to take self dot root, okay? So self dot root, if it is none, then I can just return none or false. Okay, so I'm returning false. Great. If root dot, again self dot root dot data equals to data. Okay, so I hope till now we have this habit that we know this data is different. It is present inside my root, and this data overall is different, right? If this is the case, we will return true. Great. If it is not, like if the root is not equal to data, then what we used to do, we used to use recursion. To my recursion, after comparing, I used to either call on the left or I used to call on the right. So in this case, what can I do, everyone? Pay attention. Here now I am saying that, hey, I can either call to the left or to the right. So let us do that. If data is less than root dot data, okay, and self dot root dot data, then I have to call to return search. In this, I think I should call to the left, right? Because the data is less than the root. It will be available in the left subtree. If the root is 50, then everything smaller than 50 is to the left of my tree. Now, let me call this search, okay? So I can pass the data. That is fine. How should I pass this overall? It is search is there, yeah. How should I pass this? So self dot search. Okay. In this particular code, how can I say that, hey, look only in the right part or look only in the left part? Because we are asking just for the data from the user, right? My user will not say that, hey, look, start from root. For the end user, he will just be imagining a tree. So I hope you're able to understand. Let me just explain. It's 10. Let's say 20. Let's say 0. Let's say 5, 4. Let's say 12. Okay. Now, when I ask to search for a particular value, I don't say that, hey, look at the root or start from the root. I mean the whole tree, right? So, when user will be making a object, BST object, let's say it is BST class, okay, he will be calling this search function with just the data which he wants. Let's say he wants to find 10. Now, I cannot assume or ask the user that, hey, please send maybe BST object dot root. He will not be doing that, right? That is something which I have to handle. So if the problem is clear, then I think you must be till now able to like get the solution as well. Solution is that I will create a helper because I cannot change. I cannot ask my user that, hey, you give me the overall root, the left or right. So I'm going to create a helper. In this helper, so let's say self dot search helper. I will be passing the data as it is and I will pass the root. And I can take root here. Okay. And now I should work on this root instead of self. Because if I don't do this, then I will be keeping on working on self.root, which is the topmost element of my tree. So I will keep on working on this 10 only. Okay. If I don't do this kind of a change and define a helper function, self.root will always have a value of 10. And now we can say that, hey, now using this helper function, it is analogous to what we wrote. Great. So instead of search, it will be search helper here. And I can send root dot left. Similarly, if it is not there, else return root dot right. Okay. So just a small caveat was there that we don't want our user to send me the root. We want to use it, but then also we want to use recursion. So I have to write a method or a helper method which takes in the overall things in this respect. Okay, so that was basically the idea. We can make it private as well, but I think for the timing it is not a problem. So this is how search will happen. Okay, everyone. Now let's move to insert. So talking about insert, this is something which you all are going to implement. Let's talk that, okay, how exactly are we going to insert first? Okay, great. Let's say I have to insert key, which is say 9. Okay, I have to insert 9. How exactly is the process going to go? I believe we will see if our what our root value is. Okay, let me make it blue color. Based on our root value, if the value which I want to insert in this example 9, if it is greater, then I will ask it to get inserted in my right subtree. If it is smaller, then it should be inserted in my left subtree, right? So in this case, it is smaller. So I will call on my left subtree. It will go here. It is going to call on my right subtree. It is going to call on my right subtree because 9 is greater than 0, right? Similarly for 4, it is going to call on my right subtree. Now when I reach here, when it is none, then actually we can insert it. Because normally as well, if I just uh, make a copy of this tab. So 1 second. Let me duplicate this tab. And when I normally say that, hey, insert 10, okay, or insert 9, if the root is none, then it directly inserts that, right? So what is going to happen? it is going to insert and return back the new root or this particular node which we have to connect. Okay, everyone. So I hope you are able to understand what exactly we have to do. Here, we just have to make sure that if the data is less, we ask the left subtree to handle that. If it is more, we ask the right subtree to handle that. Okay. Straightforward. It's all almost on the similar line of search. Just that this time we will not return true or false. We are going to ask recursion and a node will be created at the right position. Okay. So I want all of you to just try to implement it once. And in the next video, we will see the solution and also how to handle the use case of delete. Okay, so great everyone, do give it a try and we will meet in the next video where we will see how insert can be done and if delete is also that simple. Okay.